Hello everyone, my name is Jaisha. Today I will be presenting 5-stage pipeline Altera NIOS 2 processor which I have designed under the guidance of Professor Cheng Chu. The objective of this project is to design and implement 5-stage NIOS 2 Altera processor for given sets of instructions. This presentation will help in understanding the basic concepts of computer architecture. In this presentation, we'll first see what NIOS 2 processor is and then we'll move on to the 5-stage pipeline NIOS 2 processor. First, let us go through background. Embedded processor represents an important trend in digital embedded electronic systems. Embedded processors are system on chip with more than one processor. In FPGA-based embedded processor systems, the most widely used FPGA processors are made by one of the two main FPGA companies, Xilinx or Altera. However, there are many advantages of processors made by Altera and hence they are preferred over Xilinx processor. NIOS, Altera's first configurable 16-bit embedded processor for its FPGA product, is simple, streamlined, highly scalable RISC architecture. Over the time, architecture has evolved, acquired new technologies, and developed robust ecosystems and comprehensive industry support. This led to the evolution of NIOS 2 processor. Now let us see what is NIOS 2 processor. NIOS 2 is 32-bit RISC embedded processor which is an evolution of previous 16-bit NIOS architecture. Compared to the first generation NIOS processor, it delivers higher performance, lower FPGA resource utilization, closer integration with real-time operating systems. The NIOS 2 family consists of three members: fast, economy, and standard, each optimized for specific price and performance, as you can see from the given figure. All three cores use the same instruction set architectures and are 100% binary code compatible. NIOS 2 processor is suitable for a wide range of embedded computing applications from DSP to system controls. Now we will see NIOS 2 architecture. NIOS 2 architecture is also known as Harvard architecture. It has separate instruction and data bus, each of 32 bits. It supports basic arithmetic and logic operation with optional support for integer multiplication. The word length of NIOS 2 processor is 32 bits. All registers are 32 bits long. The byte address in 32-bit word are assigned in Little Endian style. Going further, now we will see register structure of NIOS 2. NIOS 2 has 32-bit general purpose register, out of which the register 0 and register 31 are of importance. Register 0 is referred to as 0 register and it always contains constant 0. Thus reading this register returns the value 0 while writing to it has no effect. Whereas register 31 is used to hold return address when the subroutine is called. And there are other few general registers which you can see in the given table. And the addressing modes for the NIOS 2 architecture. There are basically 5 addressing modes which NIOS 2 architecture has. Those are immediate mode, register mode, displacement mode, register indirect mode, and absolute mode. In immediate mode, 16-bit operand is given explicitly in instruction. This value may be sign extended to produce 32-bit operand in instructions that perform arithmetic operations. However, register mode is as operand in a processor register. The displacement mode is effective address. In the displacement mode, the effective address of operand is the sum of contents of register and signed 16-bit displacement value given in the instruction. The register indirect mode as effective address of operand is the content of the register specified in the instruction. This is equivalent to displacement mode where displacement value is equal to 0. In absolute mode, the 16-bit absolute address of an operand can be specified by using displacement mode with register 0 which always contains value 0. Now we will see the exact working of NIOS 2 architecture. This slide shows the block diagram of 5-stage pipeline NIOS 2 architecture. Here we can see that instruction register is forwarded through each stage to achieve the correct pipeline functionality. Also, the output of each stage is flopped and passed on to the next stage. Now we will see in detail the working of this architecture. There are basically 5 stages of pipelining. The first stage is instruction fetch, then there is the instruction decode stage and instruction execute stage, memory access and the write back stages. Now we will see what each stages do. The instruction fetch is the first stage in the processing of NIOS 2 processor. In this, the 32-bit address from program counter is sent to 32-bit instruction memory and the instruction stored on the corresponding address is given to the output of the decode stage. Also, the program counter is incremented by 4 unless there is a branch or no instruction. Then there is the instruction decoding stage. It is the second stage in which it takes the instruction given by the instruction memory. It decodes the instruction and extracts the information like what is the operation to be performed, what are the operands, that arguments and destination registers where the results after computations or execution is stored. Also, register bank is initialized in this stage. And in case of I-type instruction, 16-bit immediate value is sign extended to 32-bit and is the input to program counter in case of branch instruction. Also, this sign extended 32-bit along with 2 operands register are forwarded to the next stage. The instruction execute stage is a third stage. It takes the input from the register bank which is fed by the register's address indicated by the instruction to be executed. The one of the 2 operands and the sign extended 32 bits are passed through the mux depending on the select line. In our case, the R type or I type. Then the data selected by the mux and other operand from the execute stage is inputted to ALU and depending on the opcode computation is carried out. The memory access stage is the fourth stage. In this stage we are accessing the memory. Not all the instructions are going to access the memory. This stage comes into picture only when load or store operation has to be performed. The output of ALU is stored in the memory stage and also the data of target register which has to be stored in the memory for the stored operation. The last stage is the write back stage. In this stage we are writing the data back to the register bank. This is the last stage of pipeline which stores the output of memory as read data in the case of load or store instructions and direct output from ALU for all other instructions. Now we have 5 stages, which means that at any given cycle of executing the instruction at this point, there could be 5 different instructions at various points of this NIOS 2 data path. Thus the throughput and parallelism of processor. Now we will see the major components of NIOS 2 architectures which are important for the design of hardware. These components are program counter, instruction registers, register file, arithmetic and logic unit, and the program counter is a register structure that contains address pointer value of a current instruction. Each cycle, the value at the pointer is read into the instruction decoder and program counter is updated to the point to the next instruction. For RISC computers, updating program counter register is simple as adding the machine word length to the PC. An arithmetic logic unit is a digital circuit used to perform arithmetic and logic operations. It represents the fundamental building block of central processing unit of a computer. Modern central processing units contain very powerful and complex ALUs. In addition to ALUs, modern central processing units contain control unit. Most of the operations of central processing units are performed by one or more ALUs which load the data from input registers. A register is a small amount of storage available as a part of CPU. The control unit tells the ALU what operation to perform on the data and ALU stores the result in an output register. The control unit moves the data between these registers, the ALU and the memory. Now we will see the hazards which are occurred due to the pipelining. There are data hazards and control hazards. Data hazards occur when an instruction is to be fetched whose data are dependent on the previous instructions. This hazard can be avoided by stalling the pipeline for one cycle. Also, by inserting no-op instructions and rearranging instructions, we can solve this hazard. Then there is a control hazard. This hazard occurs because we don't know the branch decision until the memory stage. Over here also the stalling helps. The stalling the pipeline till branch decision. But this is not efficient and it slows down the pipeline. Another possible solution is the branch prediction. Now we will move forward to verification part. To verify the processor, an instruction set for computing dot product of two vectors is initialized in instruction fetch state. Data memory is initialized in memory access stage, and also a simple test bench generating clock and reset signal is designed to check the functionality of the processor. The instruction set for a benchmark program is given as you can see in the slide. Then there is a data memory given where there is a value of A vectors and B vectors, and the product should be stored on the location 100. After running RTL simulation on model same Altera software and realizing the timing diagrams, we have verified the correct functionality of the processor. As you can see, the final result 580 is stored on the 100th location in the data memory. And now this is the compilation report which is obtained from the Quartus 2 software. And the working of 5-stage pipeline NIOS 2 processor architecture is successfully verified. The processor is tested using the certain sets of instructions for computing dot product of two vectors, and the correct result is achieved within the 72 clock cycles. Also, the hazards were handled by rearranging the instructions. Now moving on to future work. This design can further be optimized by implementing forwarding unit and stalling the instructions. Also, the J-type instructions like call and jump I can be added to the given instruction sets. Thank you.